Picture this. You're an archaeologist in the year 4023, sifting through the ruins of what was once New York City. 2,000 years have passed since humanity disappeared, and you're searching for evidence that our civilization ever existed. What would you find? Twisted metal corroded beyond recognition. Concrete crumbled to dust. Glass transformed into unrecognizable fragments scattered across sediment layers. Most of our greatest achievements would have vanished entirely, consumed by time's relentless appetite for destruction. Now extend that timeline. Not 2,000 years, but 2 million, or 20 million. How much evidence of human civilization would survive such vast stretches of geological time? The uncomfortable answer is almost none. And that realization leads us to a question so profound, it challenges everything we assume about our place in Earth's history. If our advanced technological civilization could vanish almost without a trace in just a few million years, how do we know we're the first? Before we proceed, we have a goal of hitting 1,000 subscribers. Help us out by subscribing to our channel so we can keep making great videos like this for you. Now, moving on. This isn't science fiction. This is the Silurian hypothesis, a thought experiment that emerged from the minds of astrophysicist Adam Frank and climate scientist Gavin Schmidt. Named after an ancient reptilian species from Doctor Who, this hypothesis forces us to confront a disturbing possibility. What if Earth has hosted advanced industrial civilizations before us? What if we're not the pioneers of technology and industry, but simply the latest chapter in a story that's been written and erased multiple times across the vast canvas of geological time? The implications are staggering. Every assumption we've made about human uniqueness, about our special place in the cosmos, about being the first to harness fire and split atoms and reach for the stars, could be nothing more than the arrogance of incomplete knowledge. We could be walking in footsteps we can't see, building on foundations we don't recognize, repeating patterns that have played out countless times before in Earth's deep history. But here's what makes this truly unsettling. It's not that Frank and Schmidt believe ancient civilizations existed. In fact, they explicitly state they strongly doubt any previous industrial civilization existed before our own. The terrifying beauty of the Silurian hypothesis lies not in its claims, but in its questions. It asks whether modern science would even be capable of detecting evidence of a prior advanced civilization if one had existed millions of years ago. And the answer they discovered is both humbling and haunting. The geological record, that massive library of Earth's history written in stone and sediment, has enormous gaps. Imagine trying to reconstruct the complete works of Shakespeare from a few scattered pages that survived a fire. That's essentially what paleontologists and geologists face when trying to read Earth's ancient story. Fossilization is an extraordinarily rare event that requires very specific conditions. An organism must die in just the right place, at just the right time, under just the right circumstances to be preserved for millions of years. The numbers are sobering. Scientists estimate that less than 5% of all species that have ever lived on Earth are represented in our current fossil collections. 5%. And that's just biological life, organisms that were specifically adapted to leave behind preservable hard parts like bones, shells, and teeth. Now imagine trying to find evidence of technology, of industry, of civilization. Materials that were never designed by evolution to survive geological timescales. Most of Earth's surface is geologically young. The constant recycling of crustal material through plate tectonics means that the ocean floors, which represent roughly 70% of Earth's surface, are nowhere older than about 200 million years. The continents fare slightly better, but even there, the exposed surface rocks are predominantly from the last few 100 million years. Anything older has been buried, metamorphosed, or eroded away by the relentless processes that reshape our planet. This creates what scientists call a temporal bias in the geological record. The further back in time you look, the less evidence survives. It's not because less was happening in the distant past. It's because time itself is destructive. Every year that passes, every storm that rages, every earthquake that shakes the ground, every glacier that advances and retreats, erases a little more of the ancient world. Time doesn't just heal all wounds, it erases all evidence. Consider the oldest rocks on Earth's surface. They're about 4 billion years old, roughly the same age as the planet itself. But these ancient survivors are incredibly rare, preserved only in a few special locations where geological conditions happen to protect them from destruction. The vast majority of Earth's surface has been completely renewed multiple times over. If an advanced civilization had existed 500 million years ago, the chances of finding direct evidence of their cities, their machines, their monuments would be essentially zero. But the Silurian hypothesis goes deeper than just the problems of preservation. It forces us to examine what we mean by evidence itself. When we think about how we might detect an ancient civilization, our minds immediately jump to artifacts, pyramids, statues, tools, buildings. But these direct traces are exactly what geological time is most efficient at destroying. Metals corrode, stone crumbles. Even the most durable materials we've created have lifespans measured in thousands or tens of thousands of years, not millions. So Frankenschmidt approached the question differently. Instead of looking for the civilization itself, they asked what indirect signatures an industrial society might leave behind. What changes to Earth's systems would be detectable millions of years later? What fingerprints would persist long after the hands that made them had turned to dust? The answer lies in chemistry, in isotope ratios, in the subtle but measurable ways that industrial activity alters the fundamental composition of Earth's atmosphere, oceans, and crust. An advanced civilization doesn't just build things, it moves materials around on a planetary scale. It burns fossil fuels, releasing carbon that's been locked away for millions of years. It mines metals, concentrating them in ways that nature never would. It creates synthetic compounds that don't exist in the natural world. These chemical signatures can persist far longer than any building or machine. They get incorporated into sediments, locked into ice cores, embedded in the geological record as permanent markers of artificial activity. It's like a chemical fossil, an invisible monument to industrial processes that continues to exist long after the civilization that created it has vanished. The researchers found their inspiration in an event that happened 55 million years ago, during what's called the Paleocene-Eocene thermal maximum, or PETM. This was a period of rapid global warming that saw Earth's temperature rise by more than 5 degrees Celsius in just 15 to 20,000 years. The cause was a massive injection of carbon into the atmosphere, more than 2,000 gigatons worth. That's 1 billion tons, released in what amounts to an instant in geological terms. The PETM left clear signatures in the rock record, distinctive isotope ratios in ancient soils, chemical compositions in sediment layers that stand out like neon signs against the background of normal geological processes, ocean acidification markers, evidence of widespread biological disruption and species turnover. All of this is still detectable today, 55 million years later, because the changes were so rapid and so dramatic that they overwhelmed Earth's normal buffering systems. Here's the chilling parallel. The PETM represents exactly the kind of environmental impact an industrial civilization might produce. Rapid carbon release, global warming, ocean acidification, ecosystem disruption. The only difference is timescale. The PETM unfolded over tens of thousands of years. An advanced technological society could compress similar environmental changes into centuries or even decades. But this raises an even more disturbing question. How do we know the PETM was natural? The standard explanation involves massive volcanic activity, the release of methane from ocean sediments, or other purely geological processes. But what if it wasn't? What if the PETM represents the chemical fossil of an ancient industrial civilization that pushed their planet's climate system past a tipping point? It's a thought that makes you look at the geological record with new eyes. Every rapid environmental change, every anomalous isotope signature, every period of accelerated species extinction becomes a potential clue, not necessarily evidence of ancient civilizations, but reminders of how little we actually know about Earth's deep history and how much could be hidden in the gaps of our understanding. The nuclear age has given us new tools for thinking about these deep time signatures. When we split atoms, we don't just release energy, we create isotopes that don't exist in nature, at least not on Earth. Plutonium-244, for instance, can only be produced in supernovas or nuclear reactors. If we found evidence of this isotope in ancient rock layers, it would be an unmistakable signature of technological activity. Similarly, the synthetic compounds we've created, from plastics to industrial chemicals to artificial fertilizers, have chemical signatures that would be recognizable millions of years from now. They represent a kind of chemical graffiti, artificial molecules spray-painted across Earth's natural systems in ways that natural processes could never replicate. The implications extend beyond Earth itself. If an ancient terrestrial civilization had developed space travel, they might have left artifacts on the Moon or Mars. Unlike Earth, these worlds lack the aggressive geological processes that erase surface features. A structure built on the lunar surface could theoretically remain detectable for billions of years. The Moon is essentially a museum of solar system history, preserving evidence that would have been destroyed long ago on our geologically active planet. This possibility has captured the imagination of researchers like Jason Wright at Penn State University, who seriously considers the prospect of finding evidence of ancient technological civilizations preserved on other worlds. It's not just speculation. It's a logical extension of the preservation principles that guide all archaeological and paleontological research. If you want to find old things, you look in places where old things are most likely to survive. But the Silurian hypothesis serves another purpose beyond just asking whether we're alone in time. It forces us to confront the limitations of our own knowledge and the assumptions we make about the uniqueness of human civilization. We've become so accustomed to thinking of ourselves as the pinnacle of evolution, the first and only species to develop technology and industry, that we rarely question whether this assumption is actually supported by evidence or just by the absence of evidence. The fossil record, for all its richness and complexity, represents an incredibly biased sample of life on Earth. It preferentially preserves certain types of organisms in certain types of environments during certain periods of time. The vast majority of life that has ever existed on our planet left no trace whatsoever. If biological life, which evolution specifically shaped to leave preservable hard parts, is so poorly represented in the fossil record, what chance would technological artifacts have? This creates what Frank and Schmidt call a profound detection problem. We're essentially blind to most of Earth's deep history, peering through keyhole glimpses of time separated by vast stretches of missing data. And in those gaps, entire chapters of planetary history could be hidden. Not just the rise and fall of species, but the rise and fall of intelligence itself. The timeline of this blindness is staggering. Earth has been continuously habitable for nearly 4 billion years. That's 4,000 million years of stable conditions capable of supporting complex life. During that vast expanse of time, Evolution has experimented with countless forms and strategies. It's produced organisms that can navigate by magnetic fields, communicate through electrical pulses, construct elaborate social structures, and solve complex problems. The ingredients for intelligence have been present for billions of years, yet we only have clear evidence for technological intelligence emerging once in the last few 100,000 years with humans. But what if that's not because intelligence is rare? What if it's because the evidence of previous intelligent species has been systematically erased by geological time? Consider how quickly our own technological signatures could disappear. If human civilization ended tomorrow, how long would it take for our cities to crumble, our satellites to fall from orbit, our nuclear waste to decay to undetectable levels? The answer depends on what you're measuring. Some of our impacts would persist for millions of years. The carbon we've released into the atmosphere will leave isotopic signatures in sediments for geological ages. The plastic polymers we've created will persist in certain environments far longer than our bones. The mass extinction we're currently causing will show up in the fossil record as clearly as the asteroid impact that killed the dinosaurs. But the structures we're most proud of, the monuments we think define our civilization, would vanish with shocking speed. Concrete has a lifespan measured in centuries, not millennia. Steel corrodes, glass shatters and weathers. Even Mount Rushmore, carved into solid granite, would be unrecognizable after a few million years of erosion. The forces that shape Earth's surface operate on scales that make human engineering seem as temporary as sandcastles. This realization led Frank and Schmidt to look beyond traditional archaeological approaches. Instead of searching for artifacts, they began thinking like forensic scientists examining a crime scene millions of years after the fact. What trace evidence would remain? What chemical fingerprints would persist? What changes to Earth's systems would be detectable long after their cause had vanished? The search for these signatures requires a sophisticated understanding of Earth's natural baseline. To detect artificial changes, you first need to know what natural looks like. This is where the study becomes both fascinating and frustrating. Earth's climate and chemistry have varied dramatically throughout its history, driven by volcanic activity, asteroid impacts, changes in solar output, and the evolution of life itself. Distinguishing between natural variations and artificial ones becomes an exercise in detective work that would challenge even Sherlock Holmes. Take atmospheric composition, for instance. Earth's atmosphere has undergone radical transformations multiple times throughout its history. The Great Oxidation Event 2.5 billion years ago fundamentally altered atmospheric chemistry when cyanobacteria began producing oxygen as a waste product. This change was so dramatic, it caused a mass extinction of organisms that couldn't tolerate the new oxygen-rich environment. If we can find evidence of this biological revolution in ancient rocks, what other atmospheric revolutions might be hidden in the geological record? The nuclear signatures present perhaps the clearest potential evidence. Natural nuclear processes do occur on Earth, but they're incredibly rare and leave distinctive fingerprints. The natural fission reactors at Oklo in Gabon, which operated about 2 billion years ago, demonstrate how nuclear processes can leave lasting isotopic signatures. These ancient reactors consumed uranium and produced characteristic ratios of fission products that are still detectable today. But artificial nuclear processes create different signatures. Nuclear weapons testing has scattered distinctive isotopes across the globe. Nuclear power generation produces waste products with characteristic signatures that differ from natural radioactive decay. Most tellingly, certain isotopes like plutonium-244 simply don't occur naturally on Earth in any significant quantities. Finding these isotopes in ancient sediments would be like finding a smoking gun at a crime scene. The challenge is that many of these artificial isotopes have relatively short half-lives. Plutonium-244 has a half-life of about 80 million years, which sounds long, but becomes problematic when you're looking back hundreds of millions of years. An ancient civilization that developed nuclear technology 200 million years ago would have left isotopic signatures that have now decayed below detectable levels. This temporal decay of evidence creates what researchers call a detection horizon. The further back in time you look, the fewer types of evidence survive. Direct artifacts disappear first, within thousands to millions of years. Chemical signatures persist longer, but eventually fade. Only the most dramatic planetary scale changes, the ones that fundamentally alter Earth's systems, can be detected across hundreds of millions of years. But here's where the Silurian hypothesis becomes truly mind-bending. It suggests that our detection horizon might be hiding not just one ancient civilization, but potentially many. If technological intelligence has emerged multiple times throughout Earth's history, each separated by tens or hundreds of millions of years, we might be living on a planet where civilizations have risen and fallen like waves on a beach, each one erasing the traces of those that came before. The mathematical possibilities are staggering. If we assume that conditions suitable for technological intelligence have existed for even just the last billion years, and if we allow for civilizations to emerge, flourish, and disappear on timescales of millions of years, there could have been hundreds or even thousands of technological species in Earth's past, each one convinced, as we are, that they were the first to split atoms and reach for the stars. This perspective fundamentally changes how we think about our place in the universe. We've grown accustomed to asking whether we're alone in space, whether intelligent life exists on other planets orbiting distant stars. But the Silurian hypothesis asks a different question entirely. Are we alone in time? Are we the first technological species on our own planet, or simply the latest in a long succession of civilizations that have discovered fire, developed agriculture, built cities, and reached for the sky? The search for ancient techno-signatures has begun to influence how we study our own planet's history. Researchers are developing new techniques for detecting artificial chemical signatures in ancient sediments. They're looking for anomalous isotope ratios that might indicate industrial activity. They're examining periods of rapid environmental change with fresh eyes, asking whether natural explanations fully account for the evidence. Some of the most intriguing possibilities involve what scientists call rare earth elements. These are metals with unique properties that make them essential for modern technology, but extremely rare in Earth's crust. A technological civilization would necessarily concentrate these elements in ways that natural processes never would. Finding unusual concentrations of rare earth elements in ancient sediments could indicate industrial activity, like discovering a cache of refined tools in an archaeological dig. The plastic pollution currently filling our oceans provides another model for thinking about long-term preservation. Certain synthetic polymers are essentially indestructible on human timescales and could persist in the geological record for millions of years. An ancient civilization that developed similar materials might have left plastic fossils embedded in sedimentary layers, waiting to be discovered by future geologists who know what to look for. But perhaps the most profound insight from the Silurian hypothesis isn't about ancient civilizations at all. It's about us. By forcing us to think about what signatures our own civilization will leave behind, it provides a mirror for examining our current impact on the planet. The changes we're making to Earth's climate, chemistry, and biology are exactly the kinds of signatures that could persist for millions of years. We are, in effect, conducting a real-time experiment in creating techno-signatures. The carbon dioxide we're pumping into the atmosphere will leave isotopic fingerprints in sediments for geological ages. The mass extinction we're causing will show up in the fossil record as clearly as any asteroid impact. The synthetic compounds we're creating will persist as chemical fossils long after our cities have crumbled to dust. In a strange way, this makes us both the detectives and the suspects in the case of ancient civilizations. We're developing the techniques to search for evidence of past technological species, while simultaneously creating the very signatures that future scientists might use to detect our own existence millions of years from now. The implications stretch beyond Earth itself. As we develop more sophisticated techniques for detecting biosignatures and technosignatures on exoplanets, the lessons learned from the Silurian hypothesis become increasingly relevant. If we can barely detect evidence of ancient civilizations on our own planet, how realistic is it to expect clear signals from technological species orbiting distant stars? This humbling realization is reshaping how astronomers approach the search for extraterrestrial intelligence. Instead of looking only for obvious signals like radio transmissions or megastructures, researchers are beginning to consider subtler signatures, atmospheric pollution, unusual concentrations of industrial byproducts, chemical fingerprints that indicate planetary-scale engineering projects. The James Webb Space Telescope and other next-generation instruments are already capable of detecting complex atmospheric chemistry on distant worlds. They can identify water vapor, carbon dioxide, methane, and other molecules in the atmospheres of planets hundreds of light years away. It's not inconceivable that these same instruments could detect the atmospheric signatures of industrial activity if such civilizations exist and are active during our brief window of observation. But the temporal challenge remains. Even if technological civilizations are common in the universe, the chances of detecting them depend critically on timing. If most technological species follow patterns similar to what the Silurian hypothesis suggests for Earth, they might exist for relatively brief periods separated by vast stretches of time. We could be looking at a galaxy full of planets where civilizations have risen and fallen countless times, but we're only capable of detecting the ones that happen to be active right now. This creates what some researchers call the synchronicity problem. Not only do we need to be looking in the right place, we need to be looking at the right time. If technological civilizations typically last for thousands or millions of years before disappearing, and if they're separated by tens or hundreds of millions of years, then the universe might be full of evidence we're simply missing, because we're looking too late or too early. The concept becomes even more unsettling when you consider the speed at which technological development accelerates. Human civilization went from the first powered flight to landing on the moon in just 66 years. From the invention of the transistor to smartphones in less than a century. From the discovery of DNA to genetic engineering in a few decades. This exponential acceleration suggests that once a species crosses the threshold into advanced technology, they might reach incredible capabilities very quickly. But what happens next? Do they transcend their physical limitations and leave the planet behind? Do they merge with their technology in ways that make them unrecognizable? Do they engineer themselves into forms that no longer require the industrial infrastructure that first enabled their advancement? Or do they simply burn too bright and too fast, consuming their resources and destabilizing their environment until collapse becomes inevitable? Each of these possibilities would leave different signatures in the geological record. A civilization that transcended physical existence might leave behind only the brief industrial phase of their development. A few million years of chemical fingerprints before they evolved beyond the need for mining, manufacturing, and massive energy consumption. A species that engineered biological solutions to technological problems might develop in ways that left no artificial signatures at all, returning to patterns indistinguishable from natural evolution. The most disturbing possibility is the one that hits closest to home. What if technological civilizations are inherently unstable? What if the same capabilities that allow a species to split atoms and reshape continents also give them the power to destroy themselves? The nuclear weapons we've created could end human civilization in hours. The climate changes we're triggering could make our planet uninhabitable within centuries. The biological weapons we're developing could unleash pandemics that dwarf anything in natural history. From this perspective, the absence of obvious ancient civilizations becomes less mysterious and more ominous. Perhaps technological intelligence is common, but technological wisdom is rare. Perhaps the universe is littered with planets where species reached for the stars only to fall back to Earth in radioactive ruins. Perhaps we're walking not just in invisible footsteps, but through an invisible graveyard. This interpretation of the Silurian hypothesis transforms it from an academic exercise into a warning. If previous civilizations have risen and fallen on Earth, what can we learn from their apparent fate? What mistakes are we repeating? What patterns are we following that might lead to the same end? The challenge is that the evidence, if it exists, is written in a language we're only beginning to learn. Reading the chemical signatures of ancient atmospheric composition requires techniques that didn't exist a generation ago. Detecting artificial isotope ratios in sediments demands precision that pushes the boundaries of current technology. We're essentially trying to solve a crime using forensic methods that are still being invented. But the search is already yielding unexpected insights. Researchers have identified periods in Earth's history when atmospheric composition changed far more rapidly than traditional models predicted. Some of these events coincide with mass extinctions, suggesting connections between environmental disruption and biological collapse that we're only beginning to understand. While these changes might have natural explanations, they also fit the pattern of what rapid industrial development might produce. The Permian Triassic extinction, which occurred about 250 million years ago, eliminated roughly 90% of marine species and 70% of terrestrial vertebrates. The cause is still debated, but evidence points to massive volcanic activity that acidified the oceans and poisoned the atmosphere with hydrogen sulfide. The extinction was so severe that it took millions of years for biodiversity to recover. But what if the volcanic explanation is incomplete? What if an ancient civilization's industrial activities triggered or accelerated the environmental changes that led to the extinction? The timescales involved make it impossible to distinguish between natural and artificial causes, but the pattern, rapid environmental degradation followed by civilizational collapse, is exactly what the Silurian hypothesis would predict. This uncertainty extends to other major transitions in Earth's history. The Cambrian explosion, when complex multicellular life suddenly diversified about 540 million years ago, might represent the aftermath of an earlier extinction event. The oxygen catastrophe that poisoned Earth's early atmosphere might have been preceded by civilizations that couldn't adapt to the changing chemistry. Each major transition in the geological record could hide the signature of technological species that pushed their environment past a tipping point. The implications reach beyond paleontology into philosophy and ethics. If Earth has hosted multiple technological civilizations, each one convinced of their own uniqueness and permanence, what does that say about the meaning of our achievements? Are we building monuments to human ingenuity, or simply adding another layer to a palimpsest that has been written and erased countless times? The question becomes particularly acute when we consider our current trajectory. We're in the midst of what many scientists call the sixth mass extinction, with species disappearing at rates not seen since the asteroid impact that killed the dinosaurs. We're altering atmospheric composition faster than any known natural process. We're creating synthetic compounds that will persist in the environment for geological ages. We're essentially conducting a real-time experiment in becoming a detectable ancient civilization. Future geologists studying sediment cores from our era will find clear evidence of human activity. The isotopic signatures of fossil fuel combustion, the chemical fingerprints of industrial agriculture, the plastic particles that have infiltrated every ecosystem on the planet, the radioactive fallout from nuclear weapons testing. These signatures will persist long after our cities have crumbled and our satellites have fallen from orbit. In this sense, we're already ancient. The changes we're making today will be visible to any intelligence that examines Earth's geological record millions of years from now. We've crossed the threshold from biological to technological evolution, and there's no going back. The question is whether we can navigate the transition successfully, or whether we'll join the ranks of civilizations that burned bright and faded fast. The search for ancient techno-signatures has practical implications for understanding our own future. By studying how environmental changes propagate through Earth's systems, researchers are developing better models for predicting the long-term consequences of industrial activity. The same techniques used to detect artificial signatures in ancient sediments can be applied to monitoring current environmental changes and assessing their potential persistence. This research is also informing discussions about geoengineering, the deliberate manipulation of Earth's climate to counteract global warming. If we're going to intentionally alter planetary systems, we need to understand how such changes might cascade through interconnected networks of atmosphere, ocean, and biosphere. The geological record provides the only long-term data on how Earth responds to rapid environmental change, whether natural or artificial. But perhaps the most important insight from the Silurian hypothesis is the humility it demands. We've grown accustomed to thinking of ourselves as the pinnacle of evolution, the first species to transcend biological limitations and reshape our environment on a planetary scale. But the more we learn about Earth's deep history, the more we realize how little we actually know about what came before us. The universe is vast in space, but it's also vast in time. Earth has been a stable platform for life for nearly 4 billion years. That's 4,000 million years of opportunity for evolution to experiment with intelligence, consciousness, and technology. The idea that it only succeeded once with us in the last few 100,000 years begins to seem less like a fact and more like an assumption based on incomplete evidence. This perspective doesn't diminish human achievements. If anything, it makes them more precious. Whether we're the first technological species or the latest in a long line, we're still the only ones here now. We're still the only intelligence we know of that's capable of reading the geological record, detecting ancient signatures, and asking these profound questions about our place in time. The responsibility that comes with this knowledge is enormous. If previous civilizations have failed to navigate the transition from biological to technological existence, then our survival depends on learning from their apparent mistakes. If we're truly the first, then our choices will set the template for all technological species that might follow. The Silurian hypothesis forces us to think beyond the immediate future, beyond the next election cycle or quarterly earnings report, to consider our legacy on geological timescales. What signatures will we leave behind? What story will future intelligences read in the chemical composition of our sediments? Will they find evidence of a species that learned to balance technological power with environmental wisdom? Or will they discover another layer in the palimpsest of failed civilizations? These questions don't have easy answers, but they're the right questions to ask. They force us to confront the possibility that our current path, the relentless pursuit of growth and consumption that has defined industrial civilization, might not be sustainable on geological timescales. They suggest that true success for a technological species might not be measured in the size of its cities or the power of its weapons, but in its ability to persist, to find equilibrium with its environment, to become a permanent part of its planet's story rather than a brief and violent interruption. The search for evidence of ancient civilizations continues, driven by increasingly sophisticated techniques and a growing understanding of how geological processes preserve and destroy information. Each new discovery, each refined method, each deeper understanding of Earth's systems brings us closer to answering the fundamental question: are we alone in time, or are we simply the latest chapter in a story that has been written many times before? But regardless of what we find, the exercise itself is valuable. It forces us to examine our assumptions, to question our place in the universe, and to consider our responsibility to the future. Whether we're the first technological species or the 100th, we're the only ones who can make choices about what comes next. And those choices will determine whether future geologists find evidence of a civilization that learned to thrive within planetary boundaries, or simply another layer of rock marking the end of another failed experiment in technological intelligence. The clock of geological time continues to tick, indifferent to our hopes and fears, our achievements and failures. Each day that passes adds another thin layer to the sedimentary record that will preserve our story for millions of years to come. What that story says about us depends on the choices we make right now, in this brief moment when we have the power to shape our own legacy and perhaps break the cycle of rise and fall that may have claimed so many civilizations before us. The hunt for these ancient techno-signatures has begun to reshape how we approach the deepest mysteries of our planet's past. Scientists are developing increasingly sophisticated chemical detective work, passing through sediment cores with the precision of forensic investigators examining evidence from crimes committed millions of years ago. They're looking for the molecular fingerprints that only industrial processes can create, the isotopic signatures that would stand out like neon signs against the background of natural geological processes. Consider the challenge of detecting artificial fertilizers in ancient soils. Modern agriculture depends on synthetic nitrogen compounds that don't occur naturally in the concentrations we create. These chemicals alter soil chemistry in distinctive ways, changing the ratios of nitrogen isotopes in patterns that persist long after the crops have rotted away. An ancient civilization that developed similar agricultural techniques would leave behind similar signatures, chemical ghosts of farms that fed cities we'll never see. But the temporal window for detection varies dramatically depending on what you're looking for. Organic compounds break down relatively quickly, usually within thousands to millions of years. Metal artifacts corrode and disperse, becoming unrecognizable within similar timeframes. Even the most durable synthetic materials we've created have finite lifespans when subjected to geological processes. Only the most fundamental changes, the ones that alter planetary systems themselves, have the staying power to survive across deep time. This is where the Silurian hypothesis becomes genuinely unsettling, because the signatures most likely to survive millions of years are precisely the ones associated with civilizational collapse, rapid climate change, mass extinction, atmospheric poisoning, ocean acidification. The evidence most likely to persist is the evidence of failure, of species that gained the power to reshape their world, but lacked the wisdom to do so sustainably. It's a sobering realization that connects directly to our current moment. The changes we're making to Earth's systems today, the carbon we're pumping into the atmosphere, the plastics we're scattering across every ecosystem, the nuclear isotopes we're creating, these aren't just environmental problems. They're potentially our signatures in deep time, the evidence that future scientists might use to detect our existence long after every trace of human civilization has otherwise vanished. The irony is profound. The very technologies we're most proud of, the ones that define our modern world, might be remembered primarily for their destructive potential. Nuclear power gives us clean energy, but it also gives us weapons of unprecedented destructive capability. Industrial chemistry provides materials that improve human life, but it also creates persistent pollutants that disrupt planetary systems. Fossil fuels enabled the transformation of human society, but they're also driving climate changes that could destabilize civilization itself. This dual nature of technology creates what researchers call a detection paradox. The civilizations most likely to leave detectable signatures are precisely the ones that fail to manage their technological power responsibly. A truly advanced species, one that learned to live in harmony with planetary boundaries, might develop in ways that leave minimal traces in the geological record. They might transition to renewable energy sources, develop biodegradable materials, engineer biological solutions to technological problems, essentially becoming invisible to future geological detective work. From this perspective, the absence of clear evidence for ancient civilizations might not indicate that they never existed. It might indicate that they succeeded where we're currently failing. They might have navigated the dangerous transition from biological to technological existence without triggering the kind of environmental catastrophes that leave permanent scars in the rock record. But this optimistic interpretation competes with a darker possibility. The Great Filter hypothesis proposed by economist Robin Hanson suggests that somewhere in the evolution of life from simple organisms to spacefaring civilizations, there's a step so difficult that most species never make it past. The silence of the cosmos, the apparent absence of other technological civilizations in our galaxy, might indicate that this filter eliminates most species before they can spread beyond their home planets. The Silurian hypothesis adds a temporal dimension to this concept. What if the Great Filter isn't something that happens to civilizations as they try to expand into space? What if it's something that happens repeatedly on individual planets as species gain technological power? What if Earth itself is littered with the remains of civilizations that hit the filter and never recovered? This interpretation gains credibility when you examine the mathematical relationship between technological development and environmental impact. The same exponential curves that describe improvements in computing power, energy production, and manufacturing efficiency also describe increases in resource consumption, waste production, and environmental disruption. There appears to be something inherent in technological development that creates accelerating pressure on planetary systems. Human history provides a compressed example of this dynamic. In just 2.5 centuries since the beginning of the Industrial Revolution, we've gone from burning wood and water power to splitting atoms and reshaping the global climate. The acceleration is breathtaking, but it's also terrifying. We've compressed changes that once took millions of years into decades. We're conducting a real-time experiment in how quickly a technological species can alter planetary conditions. The question that keeps researchers awake at night is whether this acceleration is sustainable. Are we approaching some kind of equilibrium where technological advancement allows us to reduce our environmental impact? Or are we following a trajectory that inevitably leads to overshoot and collapse? The geological record offers tantalizing hints, but no clear answers, because any previous civilizations that might have faced similar challenges left behind only the faintest chemical whispers of their existence. Recent advances in astrobiology have begun to provide new frameworks for thinking about these questions. The discovery of thousands of exoplanets has revealed that Earth-like worlds are common throughout the galaxy. Many of these planets have been stable for billions of years, providing ample time for evolution to produce intelligence multiple times over. If technological civilizations are as common as these discoveries suggest they should be, then their apparent absence becomes even more mysterious. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them, takes on new dimensions when viewed through the lens of the Silurian hypothesis. Perhaps technological civilizations are common, but they tend to be short-lived. Perhaps the galaxy is full of planets where intelligence has evolved repeatedly, only to destroy itself before developing the capability for interstellar communication or travel. This possibility has profound implications for how we interpret the silence of space. When we point our radio telescopes at distant stars and hear nothing but cosmic background radiation, we might not be detecting an empty universe. We might be listening to a graveyard, a galaxy full of worlds, where civilizations rose and fell before we even existed, leaving behind only chemical signatures too faint to detect across interstellar distances. The search for biosignatures on exoplanets provides another angle for approaching these questions. The James Webb Space Telescope and other next-generation instruments can detect complex atmospheric chemistry on worlds hundreds of light years away. They're looking for the chemical fingerprints of life, molecules like oxygen, methane, and water vapor that indicate biological processes. But the same techniques could theoretically detect technosignatures, the atmospheric pollutants and industrial byproducts that indicate technological activity. The challenge is distinguishing between natural and artificial atmospheric compositions. Oxygen, for instance, is a strong biosignature because it reacts quickly with other compounds and disappears from atmospheres unless constantly replenished by photosynthesis. But it's also produced by some non-biological processes, creating false positives that complicate interpretation. Industrial pollutants might provide clearer signatures of technological activity, but only if civilizations follow development patterns similar to our own. This assumption becomes problematic when we consider how different alien civilizations might be from humans. They might develop technologies based on entirely different principles, using energy sources and materials that don't exist in our experience. They might follow evolutionary pathways that lead to forms of intelligence so alien that we wouldn't recognize their artifacts, even if we found them. The signatures we're looking for might be completely wrong for detecting truly alien forms of technological development. The same problem applies to searching for ancient terrestrial civilizations. We're looking for signatures similar to the ones human civilization produces, because those are the only technological signatures we understand. But what if previous civilizations developed along completely different technological pathways? What if they never discovered fire, never developed metallurgy, never split atoms? What if they followed biological or quantum or dimensional technologies that leave no traces we would recognize? This possibility forces us to confront the limitations of our imagination as much as our detection capabilities. We're searching for ancient versions of ourselves, but intelligence might be far more diverse than our experience suggests. The signatures we're hunting for might be like looking for horse-drawn carriages on a highway full of cars. We're applying narrow assumptions about technological development to a universe that might be full of alternatives we've never conceived. But even with these limitations, the search continues to yield fascinating insights. Researchers have identified periods in Earth's history when environmental changes occurred far more rapidly than traditional models predict. Some of these rapid transitions coincide with major evolutionary innovations, suggesting connections between environmental disruption and biological change that we're only beginning to understand. The Cambrian explosion, when complex multicellular life suddenly diversified about 540 million years ago, represents one of the most dramatic biological transitions in Earth's history. Traditional explanations focus on evolutionary innovations, like the development of hard body parts and predator-prey relationships. But some researchers have begun to wonder whether environmental factors, possibly including technological activity by early civilizations, might have contributed to the rapid pace of change. This speculation pushes the boundaries of scientific respectability, but it illustrates how the Silurian hypothesis is changing how we think about major transitions in Earth's history. Instead of assuming that all rapid changes have natural causes, researchers are beginning to ask whether some might have artificial ones. It's a subtle shift in perspective, but it opens up new avenues for investigation and interpretation. The tools for conducting these investigations are becoming increasingly sophisticated. Mass spectrometry can detect isotope ratios with extraordinary precision, revealing chemical signatures that would have been invisible just a generation ago. Advanced drilling techniques can extract sediment cores from previously inaccessible locations, extending the reach of geological detective work into new temporal and geographical territories. Machine learning algorithms can identify patterns in vast data sets that human researchers might miss, potentially revealing subtle signatures of artificial activity hidden in the noise of natural variation. But perhaps the most important development is conceptual rather than technological. The Silurian hypothesis has forced scientists to think more creatively about what constitutes evidence of technological activity. Instead of looking only for obvious artifacts, researchers are developing frameworks for detecting the subtle but persistent ways that industrial civilizations alter planetary systems. These frameworks are proving valuable not just for understanding the past, but for monitoring current environmental changes and predicting their long-term consequences. The intersection between paleoclimatology and astrobiology has created new fields of investigation that didn't exist before the Silurian hypothesis was proposed. Researchers are studying how rapid environmental changes propagate through interconnected Earth systems, how biological communities respond to atmospheric disruption, and how these responses might be preserved in the geological record. This work is providing insights that extend far beyond the search for ancient civilizations. Climate scientists studying the current trajectory of global warming are finding that the geological record contains examples of rapid climate transitions that provide natural laboratories for understanding how Earth systems respond to sudden changes. Some of these transitions appear to have been triggered by volcanic activity or asteroid impacts, but others remain mysterious. The possibility that some might have technological, rather than natural causes, adds urgency to understanding how these transitions unfold and what their ultimate consequences might be. The study of mass extinctions has been similarly influenced by the Silurian hypothesis. Instead of viewing these events as purely natural disasters, researchers are beginning to consider whether some might represent the signatures of civilizational collapse. This doesn't mean that ancient aliens caused the extinction of the dinosaurs, but it does mean taking seriously the possibility that technological activity by terrestrial species might have contributed to some of the more mysterious extinction events in Earth's history. The implications extend beyond academic research into practical questions about human survival and development. If previous civilizations have indeed risen and fallen on Earth, then understanding the patterns of their collapse becomes essential for avoiding similar fates. The geological record might contain not just evidence of past failures, but lessons about how to navigate the dangerous transition from biological to technological existence. This perspective is beginning to influence discussions about sustainability, renewable energy, and global governance. Instead of viewing environmental protection as a luxury for wealthy societies, it becomes a survival imperative for any technological civilization. The stakes aren't just about preserving natural beauty or preventing inconvenient climate changes. They're about avoiding the kind of systemic collapse that might have claimed previous civilizations and ensuring that human technological development follows a sustainable trajectory. The search for ancient technosignatures is also informing efforts to develop better methods for detecting technological activity on exoplanets. If we can learn to recognize the subtle signatures of industrial activity in Earth's geological record, we might be able to apply similar techniques to analyzing the atmospheric compositions of distant worlds. This could revolutionize our approach to the search for extraterrestrial intelligence, expanding it beyond the traditional focus on radio signals to include a much broader range of potential technological signatures. But the most profound impact of the Silurian hypothesis might be philosophical rather than practical. It forces us to confront the possibility that human civilization is neither unique nor permanent. We might be just the latest experiment in technological intelligence, following patterns that have played out many times before on our own planet. This perspective demands humility about our achievements and urgency about our choices. The universe operates on scales that dwarf human experience. Stars burn for billions of years. Galaxies collide over hundreds of millions of years. Even the shortest geological processes unfold over timeframes that encompass hundreds of human generations. Against this cosmic backdrop, the entire history of human civilization becomes a brief flicker, a momentary experiment in consciousness and technology that could end as quickly as it began. This realization doesn't diminish the importance of human existence, but it does place it in a broader context. We're not just building societies and technologies for ourselves. We're potentially setting patterns that could influence the development of future terrestrial intelligence, whether human or post-human or entirely alien. Our choices about how to manage technological power, how to balance growth with sustainability, how to navigate the challenges of global coordination, these decisions might echo across geological time. The responsibility is staggering. If we succeed in creating a sustainable technological civilization, we might provide a template for future species to follow. If we fail, we might join the ranks of previous experiments in intelligence that burned bright and faded fast, leaving behind only chemical signatures and cautionary tales written in stone. The search for evidence of ancient civilizations continues, driven by curiosity about our past and concern about our future. Each new technique, each refined analysis, each deeper understanding of how Earth systems preserve and destroy information brings us closer to answering fundamental questions about intelligence, technology, and survival on cosmic scales. But regardless of what we find, the exercise itself is transforming how we think about our place in time and space. We're learning to read the Earth as a book whose pages extend back billions of years, whose chapters might contain stories of intelligence and civilization we never imagined. We're developing tools to detect the faintest whispers of technological activity across geological time, and in doing so, we're gaining new appreciation for the remarkable feat of consciousness that allows us to ask these questions at all. The Silurian hypothesis reminds us that we're temporary stewards of knowledge and capability that might have existed before and might exist again. Our task is not just to understand the universe, but to ensure that understanding survives long enough to be passed on. Whether to our own descendants or to entirely different forms of intelligence that might emerge from Earth's ongoing evolutionary experiment, we have a responsibility to be worthy ancestors, to leave behind not just chemical signatures of our industrial activity, but evidence of wisdom, sustainability, and the careful management of technological power. In the end, the question of whether humans are the first civilization might be less important than the question of whether we'll be the last. The geological record will preserve our choices long after we're gone, writing our story in isotope ratios and extinction patterns and atmospheric chemistry. What that story says about us depends on the decisions we make right now. In this brief moment, when we have the power to choose our own legacy and perhaps break the cycle of rise and fall that might have claimed so many civilizations before us. The question of whether we're alone in time becomes even more haunting when we consider the speed at which civilizations might rise and fall. The entire span of recorded human history, from the first written records to today, covers only about 5,000 years. The Industrial Revolution began less than 3 centuries ago. Nuclear weapons have existed for fewer than 80 years. In geological terms, our entire technological civilization is younger than the blink of an eye. Yet in that brief span, we've already demonstrated the power to alter Earth's fundamental systems. We've changed atmospheric composition more rapidly than any known natural process. We've triggered what many scientists call the sixth mass extinction. We've created synthetic isotopes that will persist for millions of years. We've essentially compressed the environmental impact that might naturally unfold over millions of years into a few centuries of frantic activity. This acceleration raises a disturbing possibility. What if the typical lifespan of a technological civilization is measured not in millions of years, but in thousands? What if the window between achieving industrial capability and either transcending physical limitations or destroying yourself is incredibly narrow? If that's true, then the galaxy might be littered with the remnants of species that gained the power of gods, but retained the wisdom of children. The mathematics of this scenario are sobering. If technological civilizations typically last only a few thousand years, and if they're separated by tens of millions of years, then at any given moment in cosmic history, the vast majority of habitable planets would appear lifeless. Not because they never developed intelligence, but because intelligence keeps destroying itself before it can establish a permanent foothold in the universe. This temporal isolation would explain why we see no evidence of other civilizations in our galaxy. We might be surrounded by worlds where intelligence has evolved countless times, but we're looking at them during the long quiet periods between technological experiments. The radio signals we're searching for might have been transmitted millions of years ago, or might not be transmitted for millions of years to come. We're essentially trying to catch lightning in a bottle on a cosmic scale. The fossil record of Earth provides some unsettling parallels to this pattern. Life has experienced at least 5 major mass extinctions, events so severe they eliminated the majority of existing species and reset the trajectory of evolution. Each time, life recovered and diversified, but along completely different pathways. The organisms that dominated before each extinction were replaced by entirely new forms that exploited the empty ecological niches left behind. What if technological intelligence follows a similar pattern? What if Earth experiences periodic cycles of civilizational rise and collapse, each one separated by millions of years of recovery time? The species that emerge after each reset might be completely different from their predecessors, following alternative evolutionary pathways that lead to forms of intelligence we wouldn't recognize. This possibility becomes more plausible when you consider how dramatically life on Earth has changed over geological time. The oxygen we breathe was once a deadly poison that triggered one of the planet's most severe extinction events. The continents we live on have drifted across the globe like pieces of a vast puzzle being constantly reshuffled. The climate has swung between ice ages and greenhouse conditions that would be unrecognizable today. Against this backdrop of constant change, the idea that intelligence might emerge, flourish, and disappear multiple times becomes less far-fetched. Each cycle might be triggered by different evolutionary pressures, leading to technological development along completely different lines. Some civilizations might never discover fire. Others might skip metallurgy entirely and develop biotechnology instead. Still others might pursue quantum or dimensional technologies that leave no recognizable traces. The diversity of possible technological pathways becomes apparent when you consider how different human cultures have approached similar challenges. The ancient Greeks developed sophisticated mathematical and philosophical frameworks without ever harnessing steam power. The Chinese invented gunpowder, printing, and the compass centuries before Europeans, but followed different trajectories of technological development. Indigenous cultures around the world developed sustainable agricultural and social systems that persisted for thousands of years without the environmental disruption that characterizes modern industrialization. If such diversity is possible within a single species over just a few thousand years, imagine the range of possibilities across different species over millions of years. Each experimental civilization might represent a completely different approach to the challenge of intelligence interacting with environment. Some might achieve harmony and sustainability. Others might burn bright and fast. Still others might transcend physical existence entirely, leaving behind only subtle traces of their passage. The search for these traces requires a fundamental shift in how we think about evidence itself. Archaeological methods work well for studying human prehistory because we're looking for artifacts created by organisms similar to ourselves, using materials and techniques we can understand. But detecting evidence of truly alien intelligence requires moving beyond assumptions about what technology should look like. Consider the possibility that an ancient civilization developed primarily biological technologies. Instead of mining metals and burning fossil fuels, they might have engineered organisms to serve their needs. Living buildings that grew rather than being constructed. Biological computers based on neural networks rather than silicon circuits. Transportation systems using trained or engineered creatures rather than mechanical vehicles. Such a civilization might leave behind genetic signatures rather than chemical ones. Unusual organisms with characteristics that don't fit natural evolutionary patterns. Ecosystem modifications that persist across geological time. Biological innovations that appear suddenly in the fossil record without clear evolutionary precursors. These traces would be almost impossible to distinguish from natural evolution unless we knew exactly what to look for. The challenge becomes even greater when you consider that biological technologies might be self-limiting in ways that prevent environmental collapse. A civilization that lived in harmony with natural systems might never trigger the kind of dramatic environmental changes that create clear geological signatures. They might represent the successful navigation of the technological transition that we're currently struggling with, but their very success would make them nearly invisible to future detection. This creates a profound selection bias in what kinds of ancient civilizations we're most likely to detect. The evidence that survives best across geological time is evidence of failure, of species that gain technological power, but lack the wisdom to use it responsibly. The civilizations most likely to leave detectable traces are precisely the ones that destroyed themselves through environmental mismanagement. From this perspective, the absence of clear evidence for ancient technological civilizations might actually be encouraging. It might indicate that most species that reach our level of development successfully navigate the transition to sustainability. They might learn to live within planetary boundaries, developing technologies that enhance rather than disrupt natural systems. Their invisibility in the geological record might be a sign of success rather than absence. But this optimistic interpretation competes with mounting evidence that our own civilization is following the dangerous pathway toward environmental collapse. The changes we're making to Earth's climate, chemistry, and biology are accelerating rather than stabilizing. We're consuming resources faster than they can be replenished, producing waste faster than it can be processed, and altering environmental conditions faster than ecosystems can adapt. The parallel with previous mass extinctions is becoming increasingly difficult to ignore. Each of the major extinction events in Earth's history was triggered by rapid environmental change that overwhelmed the adaptive capacity of existing species. The current rate of species loss rivals or exceeds the pace of these ancient catastrophes, suggesting that we might be in the early stages of triggering the sixth mass extinction. What makes this particularly ominous from the perspective of the Silurian hypothesis is that we're simultaneously the cause of the environmental disruption and its primary victim. Unlike asteroid impacts or volcanic eruptions, which strike randomly, the changes we're making to Earth's systems are self-inflicted. We have the knowledge to understand what we're doing, the technology to monitor our impact, and theoretically, the capability to change course. Yet we continue down a path that seems to lead towards civilizational collapse. This pattern of self-destructive behavior in the face of obvious consequences might be a universal characteristic of technological intelligence. The same cognitive traits that enable scientific discovery and technological innovation might also create psychological blind spots that prevent effective long-term planning. The ability to manipulate abstract concepts might come packaged with overconfidence in our ability to control complex systems. The drive to explore and exploit might be inseparable from the tendency to overconsume and overshoot environmental limits. If this psychological package is indeed universal among technological species, then the Great Filter might not be an external obstacle, but an internal one. The challenge might not be developing sufficient technology to survive and spread, but developing sufficient wisdom to manage that technology responsibly. Intelligence might be common in the universe, but intelligent restraint might be rare. This interpretation gains support from the study of other complex systems that exhibit similar patterns of rapid growth, followed by collapse. Bacterial colonies in laboratory cultures grow exponentially until they exhaust their nutrients and poison themselves with their own waste products. Economic bubbles expand until they burst from their own internal contradictions. Even computer simulations of artificial life show tendencies toward boom and bust cycles when resources are abundant but finite. The question that haunts researchers studying these patterns is whether they represent universal features of complex systems, or whether they can be overcome through conscious intervention. Can intelligence recognize and transcend its own destructive tendencies, or are those tendencies so deeply embedded in the nature of intelligence itself that they're essentially unavoidable? Human history provides examples of both successful and unsuccessful attempts to manage resource consumption and environmental impact. Some cultures developed sustainable practices that allowed them to persist for thousands of years in the same locations. Others expanded rapidly and then collapsed when they exceeded the carrying capacity of their environment. The difference often seems to come down to the presence or absence of cultural mechanisms for long-term thinking and collective restraint. The challenge for global technological civilization is developing such mechanisms on a planetary scale. The same technologies that enable unprecedented prosperity and capability also create unprecedented risks and dependencies. Nuclear weapons give us the power to destroy civilization in hours. Climate change could make large portions of the planet uninhabitable within decades. Biotechnology might enable the creation of pathogens that could devastate human populations. Artificial intelligence could develop in ways that make human intelligence obsolete or irrelevant. Each of these risks represents a potential filter that could end human civilization before it fully matures, but they also represent tests of our ability to develop the wisdom and institutional frameworks necessary to manage dangerous technologies responsibly. The outcome might determine not just whether humans survive, but whether Earth gets another chance at technological intelligence or joins the ranks of planets where such experiments have failed. The search for evidence of previous technological civilizations has thus become more than an academic exercise. It's become a search for precedents, for examples of how other species have navigated similar challenges. If we can find evidence that previous civilizations existed and survived, it would provide hope that the transition to technological maturity is possible. If we find evidence that they existed and collapsed, it might provide warnings about pitfalls to avoid. But perhaps the most important insight from the Silurian hypothesis is not about ancient civilizations at all, but about the nature of time itself. We're accustomed to thinking about the future in terms of human lifespans, planning decades ahead at most. But the changes we're making to Earth systems will persist for geological ages. The carbon dioxide we're releasing today will affect global climate for hundreds of thousands of years. The plastic polymers we're creating will persist in the environment for millions of years. The nuclear waste we're producing will remain dangerous for tens of thousands of years. This mismatch between the timescales of our decision-making and the timescales of our impact creates a fundamental challenge for any technological civilization. How do you make responsible choices about activities whose consequences unfold over periods vastly longer than any individual or institution has ever existed? How do you balance immediate needs against long-term risks when the long-term consequences might not become apparent for millennia? These questions become even more complex when you consider that the technologies we're developing are accelerating at an exponential pace. Artificial intelligence capabilities are doubling every few years. Biotechnology is advancing so rapidly that we can now edit genes with precision that was impossible just a decade ago. Nanotechnology is approaching the ability to manipulate matter at the atomic level with unprecedented control. Each of these advancing capabilities creates new opportunities and new risks. They might enable us to solve the environmental challenges we've created, developing clean energy sources, carbon capture technologies, and ecosystem restoration methods that could reverse centuries of damage. But they might also enable us to create new forms of environmental disruption that we haven't yet imagined, or to develop weapons and surveillance systems that could lock in authoritarian control for generations. The speed of technological change means that we're essentially flying blind into a future that's becoming increasingly difficult to predict or control. The same exponential curves that describe technological advancement also describe the acceleration of environmental change, resource consumption, and systemic risk. We're approaching what some researchers call a technological singularity, a point where the rate of change becomes so rapid that traditional planning and governance mechanisms break down. If previous civilizations have faced similar transitions, their experience might provide crucial insights about how to navigate this turbulent period. But the geological record is frustratingly silent about the details of how ancient technological experiments unfolded. We might be able to detect the chemical signatures of industrial activity or environmental collapse, but we can't read the social, political, or psychological factors that drove those outcomes. This limitation forces us to rely on our own judgment about how to proceed, using the best available evidence and reasoning to guide decisions whose consequences will unfold over timescales we can barely comprehend. We're essentially conducting a real-time experiment in technological civilization, with no clear precedents to follow and no opportunity for a trial run. The weight of this responsibility is becoming increasingly apparent to scientists, policymakers, and ordinary citizens who recognize that the choices made in the next few decades might determine the trajectory of human civilization for millions of years to come. We're living through what might be the most critical period in Earth's history since the origin of life itself, a moment when consciousness has gained the power to deliberately direct the future evolution of intelligence on our planet. Whether we use that power wisely or destructively might determine not just our own fate, but the fate of any future forms of intelligence that might emerge from Earth's ongoing evolutionary experiment. The geological record will preserve our choices long after we're gone, creating a legacy that could influence the development of intelligence on Earth for hundreds of millions of years to come. In this light, the search for evidence of ancient civilizations becomes a search for guidance about how to be good ancestors ourselves. We're looking for examples of species that successfully navigated the transition from biological to technological existence, hoping to learn from their successes and failures. But we're also creating our own example, writing our own chapter in the long story of intelligence on Earth. The question of whether humans are the first technological civilization might ultimately be less important than the question of whether we'll be remembered as a civilization that learned to balance power with wisdom, growth with sustainability, technological capability with environmental responsibility. The rocks will remember our choices long after our cities have crumbled and our satellites have fallen from orbit, preserving our story in chemical signatures that future intelligences might someday decode. What that story says about us depends on the decisions we make right now, in this brief window when we have the opportunity to choose our own legacy and perhaps break the cycle of rise and fall that might have claimed so many experiments in consciousness before us. The universe is watching, not with judgment, but with the patient curiosity of deep time, waiting to see what this latest experiment in intelligence will choose to become.